more mRNA, it infers there's more protein, it infers there's more active protein, it infers that active protein is inhibiting p53, which reduces, in blue, the amount of p53 protein, which reduces the amount of active protein, which screws up, say, apoptosis, right? So all of that is an inference that essentially the computer can do, given a model like this. And you put all these networks together, and we do a lot of inferences. Integrated pathway analysis for cancer is about combining the information that you get from every one of the genes into a more integrated view. One of the examples is, and this is mostly out of the Josh Stewart group. I think you saw he's the PI on this. For the ovarian cancer, we had 247 samples. Each one is now written, the sample is a column in here, and then we had a bunch of integrated pathway activities or pathway concepts on this side. And red is, again, overly active. Blue is underly active relative to normal. We found that the FOXM transcription network was highly activated abnormally in the ovarian samples. The network looks like this. You can see inferred activities in the inner ring. Each one of these is a patient. So there were an enormous number of patients with a strong inferred activity. Normally p53 inhibits this, but p53 was broken in almost every one of these ovarian cancers. This is late stage, stage 4 ovarian cancer. Very common. And so that kind of let go of the brakes on this, and FOX1 was then stimulating these things. Now, where FOX1 is not such a great target, aurora kinase B, polokinase 1, these are targets where there, you could put a drug inhibitor in there and try this. So this information is maybe helping a lot, understanding the perturbation that you're seeing in the tumor in the context of the pathway diagram and its action. And are these biologically meaningful? We actually tried clustering the information based on, this looks a lot, I'm sure you've seen these heat maps from microarray expression. So we tried clustering the patients based on microarray, and so did Broad, and so did the Baylor College of Medicine, and the other teams, nobody got anything. But when we clustered these based on these inferred activities after network analysis, we did get two separate groups, the purple group having a better survival. So this can be biologically meaningful, and it can get you beyond the limitations of a one type of data measurement like a microarray set by integrating data from multiple sources. That's it also lessens the difference between cell lines and actual tumors. And switching gears to the breast cancer, we recently, just a few months ago, we published a breast cancer study of TCJ. Our work was incorporated into that, and we published some separate papers with Joe Gray. And what happens sometimes when you cluster microarray or other kind of mono sources of data, and you try to come up with you have data that's mixed, some from cell lines and some from actual breast tissue. In this case, you find out that the cell lines kind of cluster. The cluster you get is growing in plastic versus really in the breast, which you don't want. And so the good news here is that we did not get that. We had all the greens are growing in plastic, and all the ochres, yellow, ochre, orangish is real breast, and they're intermingled very nicely. And in fact, the basal over here are very, very strongly distinguished. It doesn't matter whether it was growing in plastic or in a real breast tissue. It recognizes it as basal, so that's a very important feature. We think that's because we're at a higher level of biological extraction. We're not so caught up in the details of the data, the lower level data, that we might be able to get something. And I won't go through this in detail, but going into this in a little more, we can compare things like basal versus luminal within the breast samples and see which genes and which pathways are activated, and we see a cluster of genes involved in estrogen response and FOXA as differentiating these two. So down in basal, up in luminal, which is again consistent with breast cancer biology, and these other pathways, including hypoxic factor 1 and the other ones that are up in basal and down in luminal, so that distinguish perhaps these two. And finally, you can take this information either directly to the wet lab and try to do experiments on these cell lines, or gain further insights, or even maybe someday use it as a way of cancer therapy now. There are approved, approved assays based on microarray analysis that will actually affect your treatment in breast cancer. And so we can think of more sophisticated things than microarray analysis, which could someday also have a more sophisticated or focused or precision effect on your particular treatment in breast cancer. Part to do that is that you want to, in the end, this is kind of machine learning geek stuff. All we're doing is kind of clustering and looking at systematic differences so far, but in the end you want a classifier. You want a decision algorithm, as we call it in decision theory. So you want something that actually then outputs give them this treatment or give them that treatment, two-way decision, let's say, or a three-way decision. So we're actually testing an enormous number of these classification strategies. We have a giant pipeline. We use decision trees, neural networks, logistic regression, and whatever, all your favorite buzzwords. I was in machine learning before this, so I should be able to rattle off all the buzzwords really fast, but I'm blocking on some of them. Gil, you were in machine learning. SVM, thank you. We love SVMs. Okay, so all the geek terms for machine learning, we apply that, and it's just a big machine, right? It just says, okay, here's the clinical outcome you want to discriminate, between this outcome and that outcome. Now here's all the data, and come up with the best way of doing that and how accurate it is. And so this used to be kind of an obscure thing. It's now completely routine. Essentially, you press the button, you launch a bunch of machines and outcomes, your classifier, and it tells you how good, and it's cross-validated, and blah, blah, blah. The bad news is that it's not always 90%. It's a lot of the 70% stuff that's not clinically useful. So we need better measurements then. We need better understanding. But it tells you that you need that. So, summary. We need to switch to genomic medicine 1.0, at least, because we're on Internet 2.0 now, and medicine is far behind. My student Ted Goldstein has a great analogy. I can get better information about where to get a latte in my town on the internet than I can what breast cancer treatment I should get, right? It's amazing how medicine has not quite adapted. The flowers have not bloomed on the internet yet. I mean, there are a lot of attempts and so forth, but there's an enormous amount of information that could be creatively crunched with very high-powered algorithms if it were available to a larger community and if it were in greater quantities. And we need to do that. And we need to do that by establishing international standards for data storage and exchange with well-defined application programming interfaces. We need to have genomics lead by example. Yes, electronic medical records are completely screwed up, especially in the US, and that's a big morass, but instead of saying, well, we have to solve that first, screw that. We have to just do it right with genomics and show them how to solve the other problem. By example. Obviously, it's not, the private industry will not be able to blossom until there's this appropriate platform, so it is appropriate to leave the interpretive parts of it for a nonprofit or proprietary proprietary enterprise to build on it. Obviously, the social changes in terms of the reality that patients interact with other patients over the internet, they get information off the internet, they work with the internet. We should be helping them find clinical trials and so forth with this large database. And then finally, my last point, heading back into it, everything will be underpowered unless we can get away from the information silos that we currently have. These are my collaborators. Funding agencies, I really think that Broad, Washington, Baylor,